Hello YouTube, De-bodgery here. Welcome to EV Components Review. This is the macro video teardown for the Torp TC500 controller. Ignore my wires, I'm not done hacking. More is coming on that, so I guess I'll just talk about that. So right there is the TX and RX line for the Bluetooth module, which used to sit right here, and I haven't done that part yet. I'll get to that, over the next day or two. Just been busy with other things. Anyway, let's talk about parts on here. So this guy right here, this is an RS485 transceiver chip. So there are aspects of this thing which are kind of purpose done for Suron, and well, that's one of the parts. That's not something that you would typically need on a VESC controller, but in order to talk to some of the hardware on the Suron, the factory Suron, you kind of need that part on there. If you implement this on a Suron that's been upgraded in other ways, like aftermarket battery, things like that, well, that guy wouldn't be used. So again, it's optional to have it, but if you have a completely factory Suron and then you throw this on there, well, then some of this stuff actually plays into things. Anyway, that part is, wherever it is, there it is. So that is a SIPX SP3485. It is a 3.3 volt low power half duplex RS485 transceiver chip. And again, it's not needed by anything else other than, a Suron that is pretty much 100% factory. This little guy right here, so it says 1AAD on it. I don't know what this does. Some kind of an analog to digital converter, an op-amp package. I don't know. I looked up that 1AAD and didn't find it. So yeah, your guess is as good as mine. This guy right here, so you can see it says MCP 2551 on it. That is the CAN bus transceiver chip. So what a transceiver chip does is it's basically like a buffer or an isolator. So CAN bus from the outside world comes in, and this little guy right here kind of provides isolation and protection so that the other side of CAN bus, which is going into the CPU, if something bad were to happen in the outside world, this kind of stops and protects things so this doesn't get hit. And it also kind of acts like an amplifier, signal cleaner upper kind of a thing. That's what kind of the jobs of a transceiver are. Anyway, so yes, that 2551, and that's made by Microchips. You can see the little M logo on there. But yeah, it's just a high-speed CAN transceiver chip. All right, so over here, you can see this part says RC16 on it. This is a RAM chip, and I think this has to do with kind of their Band-Aid over the Grand Canyon having to fix what they did to completely, hobble this VESC controller. Anyway, so that guy, let me find you wherever I put you. There it is. So yes, that's actually a 16K or 2K by 8 RAM chip, and it's an MB85RC16V. That's its full part number. So the RC16 is the part that they put on the chip. The rest of it is like a bin number and things like that. But yeah, so this is just a 16K RAM chip. So you flash this thing or update its firmware over Bluetooth. And so I'm thinking that what they do is they store like that flash file in here first and update the CPU. And that way, if this thing bricks or whatever, they still have a copy of it here to maybe apply it again or something like that. I'm pretty sure this is here because, they've completely removed all other ways to get to the STM32 F405 that you would typically have in anything else that's VESC. The Bluetooth module, obviously, used to sit right here, and it will again after a while. But, yeah, this is a fairly inexpensive Bluetooth module, and you can see it says N51822 on it. If you want to Google for the thing, this is a very common Bluetooth module. They're very inexpensive. I'm not going to talk too much about it, other than to say that those two solder pads were right there and there, or I'm sorry, right here and here, are SWD-IO and SWD clock, which are needed for the Blackmagic software. Something I said wrong is that Blackmagic would take from the CPU and flash this, and then from here do the same thing back. It's really just a one-way street, not a two-way street. So anyway, I just had my information wrong. But anyway, that's SWD clock and SWD-IO. And those two right there are TX and RX. And that's the two that I'm going to borrow on here to go over to the VESC 75300 controller to use its Bluetooth module. So yeah, this will go back on here after a while. Once I do that hack, all right, you can see my solder work on here for those 3 wires. So the wire inside here is about 0.5 millimeters, just like the legs on here are. So this is, tiny soldering. Yeah, people can do this, obviously I did. The wires, they are fragile. The solder joints are fragile because they are in such a tiny surface area. So I secured them all down with some silicone, like I did with the CAN bus wires over here, so that they would not break off, because these wires are very, very thin. Yeah, anyway. Yep, obviously that's the STM32 F405, standard fare for VESC everywhere across the planet, almost exclusively. Right here, this is an LM5164. I'm pretty sure that's what it is. Obviously a buck chip. Yeah, LM5164. So that is a 100 volt max, 1 amp DC to DC converter chip, aka a buck chip. So takes battery voltage in, and with the those couple resistors right here, they create a voltage divider, and it tells this thing what its output voltage should be. So that's pretty much how that works. This little buck chip right here, so this TN2ET, I looked for it and I couldn't find that part, but again, this is the 5 volt DC to DC converter right here, and most likely a couple of those resistors right there are the divider circuit that tells this thing what to make its output voltage set to. And so yeah, that's the 5 volt DC to DC converter. So you can see the ST logo on this linear 3.3 volt regulator. So ST, they contracted the name on this part because this is an LD1771, I think. Hold on a second, let me look at that part real quick. I've got it, one of my thingies here. Bugger, can't find it now. There it is, LD1117. So anyway, that's a generic model, and these things come in a bunch of different voltages, 1.2 volts, 1.8, all the way up to 5 volt linear regulators. And so they contracted the name LD1117, so that's the LD part of it, and 33, meaning this is the 3.3 volt version. But yeah, this is just a 3.3 volt linear regulator. And of course you can see my 2 wires soldered to it to bring 5 volts into this board. And then of course that automatically powers up this little guy, produces 3.3 volts to turn on, or to provide power to the CPU, the Bluetooth module, and that RS485 chip. They all need 3.3 volts. So anyway, yeah, that's just a really logical place to bring in 5 volts rather than, I could have, I suppose, provided 12 volts to the 5 volt linear regulator and then let it do that, but I already had a 5 volt power supply, so just use that directly. Alright, so these are your Mosfet gate drivers, and as you can see, they're a TI part, and it's a 27211. Oops, sorry about that. Bumped the camera. So those guys are a 100 volt part, or 120 volt part. Let me find the data sheet for those things. I have it here, wherever it is. Anyway, yeah, not finding the data sheet up top. Yeah, they are rated for 120 volts max, which is about right for a controller that's a 100 volt max controller like these TC500s are. Right next to them, you can see the through holes. So that's the connections down to the power stage for bringing like current, gate control, temp sensors, all that kind of stuff up to the logic board. These are your current sense amplifiers. So one here, here, and here. So typical VESC implementation is you have current sensing on all 3 phases. And so, yeah, here is the amplifiers for that. They say 1 dV on them. I was unable to find that part. And however, there's another part that I have seen before. And let me find that guy again. I must have closed the page. Darn it. Anyway, oh, that's right. It's on a different tab. There it is. So that is probably either the exact same thing as like what Tronic uses, which is, and also ASI, which is an INA 181. You know, the pinout is the same, the package is the same, just has this 1DV on it rather than, I forget what it says, 18JD, which is the part that Tronic and ASI use. But I mean, everything here is exact same placement of components. This might very well be an INA 181 for all I know. All right, so let's flip this thing over real quick. There's nothing really to see on the back side here other than those through holes for bringing signals to and from the power stage. So that's pretty much everything there. Pretty much a blank slate on the back side. All right, so here is the power stage. So I have said that this is a really tidy power stage, and I'd have to say that is mostly true. One of the VESC engineers I talked to found something that I did not notice. So let me talk about that first. So you can see all these ceramic caps. This is fantastic. Yeah, you've got them right at each one of the Mosfets, which is super cool. You've got a bunch of extra ones here and here too. So there is a little tiny problem here. And let me show it to you on this one. These other two phases have the same thing. So you see these ceramic caps right here. Well, this right here is battery plus, and you can see this copper trace right here, and they go solder down to it. And the other side of it is right there. And that comes over here to this side of the MOSFETs on this side of the shunts. And that's wrong. These ceramic caps should go from battery plus to battery minus, and they don't. They're on the top side of the shunts, and they should be going to down here instead. So this is a flaw in the design. It basically means these guys are floating. Yeah, because they have this resistance right here that they're going through before they do any filtering. So they're not filtering correctly. They really should be going from battery plus to battery minus like those ones do. So you can see how you've got the battery minus bus. You can see you got copper trace here. And so that's the negative side, and here is the positive side going up to battery plus. These ones are done correctly, but these ones for each one of the phases are not. So yeah, like I said, when the VESC engineers spotted that, I didn't notice it. But yeah, those are done wrong because they're literally floating on top of the current shunts on each one of the phases. And that basically means these guys are floating depending on whatever phase current is in the motor. And that's weird, and it whacks up filtering considerably. So yeah, those were not implemented correctly. So you can see these three connectors. When I took it apart, all their solder joints lifted and broke off. So anyway, I had to reflow this board so that those could be reattached. And as is typical for decent quality reflow soldering, you can see that they're all straight. The pins are very uniformly soldered down. This looks like professional reflow soldering, which, you know, when you look at the stuff that like you get from KO Moto, do you see this kind of level of straightness and everything? And the answer is no. And it's obvious because you can see that they've done repairs. You can't tell that I reflow soldered those three connectors, other than the fact that there is a pin that got a little bit bent there, and obviously I said I lifted a trace. Otherwise, you would never know. You know, these ones look like they were done at the factory. So you would never know that I, Richard, reflow soldered those connectors. And that's how it should look. So yeah, obviously this needed to be repaired. You can see that the trace is lifted underneath there. So each one of these legs is 0.5 millimeter wide, you know, across. So my little wire here is also 0.5 millimeter. And yeah, I stripped off the solder resist, that's the green stuff, on top of that trace, and soldered it here into the leg to fix that little lifted trace. So that part is solved. Right there, that little part, that is your one thermistor on here. There's not one per phase, so like that right there is just a resistor. In fact, that goes right to that gate leg on that MOSFET, so that is definitely not a thermistor. But you know, this is a very tiny board, so probably that one thermistor over there is really going to cut it, and this whole thing is stuck down to a big chunk of aluminum. You know, it's not spread out a lot, say like, you know, the KO stuff, where they, again, only have one temp sensor, but it's spread across a lot of area. So there, you know, multiple temp sensors would be much more beneficial. Whereas this one here, it's very tidy, very compact, and it's, you know, this metal core printed circuit board is a beefy chunk of aluminum anyway, stuck down to an even bigger chunk of aluminum. So this is going to be pretty much adequate. Anyway, a mostly very good power stage, with a little problem with what they did with the ceramic caps, not bringing them down to battery minus. They could have. As you can see, this trace right here is literally right next to there, and they did these wrong. So odd. Anyway, yeah, that could have been done better. As you can see, here's battery plus. The tabs on these MOSFETs literally touch it, so you can't get a tighter bus than that. That's pretty damn good. This trace from here to this upper edge of the board is 18 millimeters tall, and it looks to be, I can't be sure, 1 or 2 ounce copper. It's pretty thick. So even without this brass on here, it's already really strong. So this is 11,000 times better than the best thing that KO Moto has ever done. This is a pretty good power stage with this one exception right here. This is very, very tidy. And then, you know, right here is your phase connector, and so that's literally your phase bus right there. And they can't really bring this brass piece closer to the MOSFETs than this. So this is a very narrow gap in here. And again, it's all that like 2 ounce copper. So it's pretty damn good. If they brought it any closer, they'd be touching the 2 gate legs, which are that one and that one. So they have to leave that little bit of gap on the high side MOSFETs. But yeah, this is very, very tight. And again, on the other side, you know, the tabs on the MOSFETs are literally touching the brass. So that's pretty damn good right there. And on this end here with these MOSFETs, you know, again, you've got this thick copper here, and then the shunts actually do touch the MOSFET legs on this side. So yeah, this is pretty damn good attention to detail to get things that tight. But you know, these shunts do shift a little bit, and they do have a little bit of gap. So like over here, you can see that things are shifted a little bit here and here. But still, you know, this is a very, very small gap, and you've got this nice thick piece of copper here. So I don't really have any complaints that the shunts are shifted a skosh. And then you've got some little places like we've got these slight little differences here. That's still really, really, really good. And the same thing on battery minus. From here to here, this is 18 millimeter wide copper, and then it's got this big chunk of brass on top of it. This is already a pretty good piece of copper. KO Moto could learn a ton from this power stage. Yeah, it's not perfect. You know, it does have a problem with it, but it's still a really good power stage. Yeah. Anyway, yeah, I definitely like their Torp power stage, with the one exception of how they did these ceramic caps. That's not quite good. Yeah, should have made that from battery plus to battery minus right there. Placement is perfect. Just putting them on the tops of the shunts, that's not what's right. So anyway, hope that helps some folks out. I guess I didn't tell you what those MOSFETs are. So G015N10s. I am pretty darn sure I've run across that exact same MOSFET before. Like EBMax or KO Moto or somebody else I've recently done uses that exact same MOSFET. Yeah, that's a Hawaii part. You can see their logo like right up here in the corner. That's kind of that, you know, diagonal H. But yeah, they are a 100 volt, 380 amp MOSFET with 1.2 milliohms of internal resistance from drain to source on them. So that's called RDS. Anyway, pretty decent Chinese MOSFET that I've seen in a couple different places. As you can see, this is a 12 FET controller. You're not really going to ever get 380 amps out of one of these MOSFETs, like ever. Not unless you like stick it in like liquid nitrogen. You know, in typical application, that's never going to be the case. And with 2 of them in parallel like this, you know, you're probably really pushing your luck to do like, say, 600 amps across the 2 of them. even though they are tall and even though it's a fairly good MOSFET. So I think that the specs that Torp gives for these things is probably ambitious, or maybe really what that is, it's common hype marketing language, and it's really just peak, which you can't really use. Because otherwise, this is a 6-FET controller. Let's face facts. A 24-FET controller is going to be able to deliver more current than a 6-FET. Even if it is TO220s, it's still going to outperform this. So yeah, I'm pretty sure that their specs on these things is a little ambitious, but it is a very tidy power stage, with this one exception on how they did the low side of these filter caps. Well, I think that's everything I want to show you. Hope that helps some folks out. Take care. Talk to you later.